All right. So last time on Mosaic Land, we were in a situation where we figured out what was a mosaic. So we kind of looked at it and we looked at just uh, mosaics, abbreviation of rectangles, and we have a bunch of rectangles, axis aligned rectangles within it. And we were looking at notions of a mosaic being prime. And so this mosaic's not prime, and why is that? This mosaic, can anybody tell me why this mosaic's not prime? Let's number the mosaics. So like A, B, C, D.
There's a fault line below A and B and above the rest.
All right, that's perfect. So we can separate this into these two blocks, or hell, even like just A and B itself could be separated. And we saw that the smallest prime we could create looked something like this, where we had this and we had this and we had this pinwheel type pattern, like a pattern that looks like a pinwheel. And let's say A, B, C, D, E. And this was a prime because we can't decompose this into multiple blocks. So a question that was asked was like, hey, how can we enumerate these primes and how many primes are there? And the answer was a lot of them. A lot of them. And we saw that this was the smallest prime at this, and its mirror opposite was the smallest prime. And we also saw that there's no primes of where of six blocks. So you cannot make a prime mosaic out of six blocks. And we're like, okay, that's interesting. So can we make for any future blocks? Yes, we can. Uh, and this was actually found. I didn't know this at that time, but this was found by folks in the TwoSwap Discord, uh, especially named. Let me get the usernames right. Um, Kodafy and CatCat. They found they found a good dynamic programming approach to generate all possible primes, and that's really fast. It ran really, really fast. But as you will soon figure out, that's not the ceiling of it, because these little things, these mosaics, are not just mosaics. They are much more than mosaics. And that is because they are what we call a bijection between a class of permutations called Baxter permutations. All right. Yeah. So, what is a Baxter permutation again? Um, so, before we go into what's a Baxter permutation, let's first figure out what is a permutation. So, given I have, say, n numbers going from 1, 2, 3, n, a permutation is any arrangement of these n numbers. So, for example, if n was uh, 5, so 1, 2, 3, 4, 5, a permutation of n would be, say, let's call that permutation pi n. this is a way of writing permutations. Usually people write permutations with this pi symbol a lot. Say 2, 4, 5, 1, 3. All right. Uh, does that make sense? So what I'm saying here with this is 1 goes to 2, 2 goes to 4, 3 goes to 5, 4 goes to 1, 5 goes to 3. And that's your cycle. And that's the permutation. Um, Now, why are permutations involved here? We'll get to that, but before that, let's figure out what is backdoor permutation. So this is primarily because of this one guy named Glenn Baxter. So yeah, not this guy. This is a different person. Glenn Baxter Matt. Glenn Earl Baxter. Dark mode, please, dark mode. Okay. So this person kind of discovered the vector permutations almost by accident. He was not looking for permutation research. What he was trying to do was looking at fixed points of functions. So when we map a function from like of going from 0 to 1 through to 0 to 1, you are trying to find like what functions give fixed points, how many fixed points are there, and so on and so forth. In his journey to find that, he ended up finding out this class of permutations that end up showing up in a lot of places uh, called the Baxter permutation. And a bunch of stuff. I don't want to go into the bunch of stuff. So I just want to see what like Baxter permutation means. So the Baxter permutation has only two restrictions, which is uh, I cannot have these two patterns. Let me see if did I get that right. 2, 4 1. All right, I twisted it. So 2, 4, 1, 3, and 3, 1, 4. What does this mean? This just looks like numbers. Okay. So before we go into that, let's look at this particular permutation right here. This one where we go 2, 4, 5, 1, 3. So imagine we create a square and it's a square grid of 1, 2, 3, 4, 5, and also 1, 2, 3, 4. So we saw that 1 goes to 2. So we put a dot at 1 going to 2. 2 goes to 4. Okay, so we put a dot at here. 3 goes to 5. We put a dot here. 4 goes to 1. So we put a dot here.
Hey,
And 5
you're
goes
off
to
screen, by the way.
good catch. Thank you. All right. So can you see this? Does this make sense?
Yep.
All right, perfect. So the idea is when we're saying that we want to avoid the 2, 4, 1, 3 and 3, 1, 4, 2, so we want to avoid this, right? This is what we want to avoid. So if we want to avoid this, what do? We look at every 4-length subsequence of this permutation. So we are trying to find patterns like this. We are trying to find patterns similar to So let's say this is 3, and then this is 1, this is 4, this is 2. So what we are trying to avoid is we are trying to avoid 4 numbers that are in this sequence where the third highest is first, and uh, then there's the lowest, then there's the highest, and then there's the second lowest. And the another restriction is that this particular thing implies that these two values need to be next to each other. So the lowest and the highest value need to be next to each other, but there can be gaps between this number and this number, and as well as this number and this number. So if we find any such pattern, then we are in trouble. Yeah, so they are the ordinal. Yeah, they are not the literal. They are not the literal like numbers. So they are the order of the 4 numbers. So we can so 3142 can be we can try to think of it as say we are writing it as um, third, then first, then fourth, and then second. Yes, exactly. That is why we write it as 3, then the dash 142. Uh, yeah, exactly. So some of us would also write it as 3142. So these are just notation based on like different conventions, but that's the idea. And similarly, the similar and opposite idea is 2413. So just the same thing but backward. Yeah. Permutations are permutations that avoid these two patterns. So it's a pattern avoidance. Yeah. And that is exactly what they are talking about in this particular Wikipedia page. And it's called a vincular pattern because the adjacency information, like we want the 1 and 4 to be consecutive or the 4 and 1 to be consecutive. Otherwise, that pattern is not satisfied. Exactly. We cannot have, like for any A, B, C, D, we cannot have C, A, D, B in our permutation. Exactly. And that is the restriction. That is the restriction for Baxter permutations. And as we will figure out, these permutations, there are in like a lot of them. There are, as you can see, a lot of them, and there's actually a sequence and a generating formula, like formula of that. No, B is not equals C plus minus 1. No, the values don't matter. It's just the ordering. So you take any 4 values as long as they are next to each other for the A and D are next to each other in the permutation. Uh, it doesn't matter what the values are. We'll look into examples a bit more very soon. But I just want to give the rough context around why this was important. But this was a sequence A001181 in the OEIS. Yes, this does have a lot of algebraic structure. This has so much algebraic structure. It's honestly like I'm kind of rabbit holing into this for the last 2 weeks, and I'm kind of going insane. I'm kind of going insane over like the amount of structure this has, and there's so much to do and see in this particular class of permutations, and it's relative. But yeah, so these are the sequences, and the number of permutations grow pretty big. However, if you would notice that, like, on permutations, the total number of permutations scale by n factorial, right? They scale by n factorial. But the this particular sequence scales by a power of roughly, I think, like 8 to the power n. So it scales by the asymptotics are actually like much smaller than n to the power n. So there's a much, as we increase n, the chances of a random permutation being Baxter decreases exponentially, hyper exponentially. Because again, n to the power n and 8 to the power n are two very different complexity classes. Another fun little thing is that somebody, well, not somebody, I know exactly who, but I can't pronounce their name because it's French. But they have figured out geometric, like generating functions for these patterns. And these will become very, very useful in generating the prime mosaic, the number of prime mosaics, the count of prime mosaics. Because we
I
can
think
just
that name is Dutch. If it's the Mark van Huey,
no,
I
no,
think
no,
that's
no.
that's the
The people that the people that did it was let me see, like yeah, the
um
she is
Murray.
the
I guess that's either Bouquet Malou or Bouquet Malou. I don't know if the
yeah.
S is
So
silent or not.
she has been at the forefront of research on vector permutation since forever. Also, Eric Swizzy, and there's also another person named Peltzner, yeah, Stephen Peltzner. So I have, like, they have written so many papers, like, on different varieties of it, and it's all very fascinating, as you will see in a second. So, but for now, everybody comfortable with the idea of vector permutation? Okay. Now I kind of created a thingy. Let's reset everything, and I kind of created a thingy that takes a Baxter permutation and creates a mosaic, and also a bunch of other stuff. But let's just focus on the mosaic for now. Yeah, it's a lot of. This was fun to create, very much fun to create, and it is and pseudocoded and vibe coded from that pseudocode. If you see in the CSS, if you see the telltale signs of a Claude artifact, that is where the CSS comes from initially. But again, the pseudocode is by hand, and there's been a lot of tweaks to make it like have exactly the properties I want to have. So this is a prime mosaic, and this is actually a more interesting prime mosaic than the usual prime mosaics, simply because this is, in a sense, a stronger prime mosaic. But we'll get into the strength of a prime mosaic later. First, let's figure out why this permutation that we see is this mosaic. Do you want to start with this one, or do you want to start with the smallest prime mosaic? Let's start with the smallest prime mosaic. Or hell, actually, can anybody give me a random permutation in the chat? I want to put in a random permutation. It doesn't need to be prime. Just give me a permutation. It doesn't even need to be Baxter. If it's not Baxter, we can actually examine why it's not Baxter. Just give me a, say, 7-digit permutation or a 5-digit permutation. Okay, perfect. 435,612. Let's try that. 435,612. Okay, so this becomes this particular mosaic. And this is reducible, as you can see, 3, 4, 5, 6, 1, 2, all of them are reasonable. But how did I get this particular layout from this permutation? That's the question. And to answer that, I'm basically stealing notes from Don Knuth. I will give credit where credit is due. Like this, everything I'm going to be talking about, if you want to actually hear somebody what the damn said, then go visit this particular video. And I would still like to call it mosaics, but in the literature, the mosaics are called floor plans. And I like mosaics better. I find it sounds better, so I'm gonna stick with mosaics. But wherever you see floor plans, understand a floor plan is a mosaic, and it's the same thing. But let's look at this. So we are going to show an algorithm that is not shown in the Knuth video, but it is shown in a paper that, and I'm trying to and I've tried to animate it and explore it. So let's watch it build. So let's look at the rules. Let's look at the rules. We start with the first number as one rectangle. The latest block created is the active block, and it's always going to be the current top right block. Okay? So let A be the active block and B be the incoming number. If B is less than A, then we slice the block horizontally and put B on top. And if B is greater than A, we slice it vertically and put B on the right. So in both cases, B is going to be in the top right. So and B will be the next active block. The two other rules is that if we slice it horizontally, if all the blocks to the left of B are smaller than B, or sorry, larger than B, then we extend B through those lines, through those blocks. And in a vertical split, it's just the opposite. If the block below B is smaller than B, we pretend that B is heavier and we make B grow downwards. Let's see where that takes us. So we start with 4 because that's our first number. The next block is 3. 3 is smaller than 4, so we slice it horizontally and put 3 on top. Then 5 is bigger than 3 because 3 is our active block now. If 5 is bigger than 3, we're going to slice 3 vertically or horizontally. We're going to slice it vertically. And notice what just happened. Notice what just happened. Because 5 was bigger than 4, it extended, and 4 had to make way for 5. Everybody with me so far? Yeah, like 4 and 3 are not the same height. It's because like I am calculating the height based on I'm basically cheating a bit, and I am calculating the height based on the final mosaic grid arrangement, so that I don't have to worry about changing the heights as we go along the process. So I'm basically making it all settle into the final heights and the widths, so that I have to do less work. Yeah, that's why it's not the same height. But the height doesn't really matter. Like we have to think of the mosaic as a conceptual thing with splits and edges and joins. The height can be stretched along, like you can kind of slide the rectangles along, like we visited in the last mosaic video. So the next number is 6. So 6 is going to get sliced vertically again. The next one is 1. Can anybody guess what will happen with 1?
Something will get sliced horizontally, but I lost track of how we tell which one.
Always the top right. Always the top right block.
Always the
So
top right.
what is the
Okay.
yeah? Always the top right.
So the one will end up on top.
The one will end up on top, and we didn't we wouldn't need to know if we put it above it or below it. Like for Binstruct 5, the answer is if I were to split 5 horizontally, it doesn't really matter. And we are going to see why it doesn't really matter the next time. Just after this, after I demonstrate this. So we are going to put slice 6 horizontally and put 1 on top. What else is going to happen? I'm going to revisit the rules again. And this is the rule to be thinking about. So,
so it's going to end up on top of everything?
And that's how it happens. So we check if 5 is greater than 1, so extend 1 left. 3 is greater than 1, extend 1 left. And then we hit the boundary and we stop. It's a pretty straightforward algorithm, and we are, and once we put in 2, we're finished. And we have our mosaic.
Sorry, remind me, for this, does it matter where that boundary between 1 and 2 is? Like if that's shifted over to the right?
Matter. It does not matter at all. So let's try with 6 and 5 switch. Good question. Let's see if that works. So I am going to make it play. I'm not going to step through it. And this is what the mosaic would look like with 6 and 5 switch. And
okay,
if you want, I can.
Can I just ask my question verbally, because I think that'll be easier than.
Yeah. Go ahead. Please interrupt me anytime you want. Yeah.
So my question before was, how would you know whether to put the horizontal split above or below the 3-4 split? And in this case, you chose to put the 5-6 split below the 3-4 split. If you had chosen to put it above, then the difference, I guess, would be that 3 would be your square and 4 would be a proper rectangle. And
yes, and it doesn't really matter because we can squish and stretch them as we want and still keep it valid as long as the 4 corners don't touch. So this reverse T junction and this T junction should never touch. If they touch, Don Knuth calls it the tatami condition, where the 4 tatamis are in hit one corner, and that's no good.
So you sort of are considering mosaics up to an equivalence of sliding the segments up and down. Okay,
exactly.
Okay.
Exactly. Mosaics here are they are less actual layouts and more an adjacency rules between the walls and the rectangles. And the adjacency rules part will become more evident when we look at it in terms of a graph, but that's part 2. So we can so the one that we are going to consider, and the one that is considered in most literature on floor plans or mosaics, as we call it, is that we do not allow the 4 crossing. If we allow the 4 crossing, the object becomes much harder to deal with. Yep. Yep. If you want refreshers on what mosaics are, I can quickly mention something, or again it's two top can, so that's fine. But yeah, so this is how this whole thing happens. It's kind of the algorithm is very simple. when you remember the rules, the algorithm is very simple. Uh, but so this is something that people have been circling around since forever. So I'm actually going to there's actually been a article on the American Mathematical Monthly by Robert F. Brown discussing how this was an example of mathematical research about a good question that won't go away. So, and it's actually a very interesting read. It's not really that technical. It is more the content density is more in line with the 3 cycle talk than like a full on paper. So it's just the history of how this particular problem has been motivated and been circled about by various mathematicians over time. Yeah. So it's actually a really good read, and I would recommend everybody to like check this particular article out. And it is like very fun that like TrueSwap discovered it independently, because it just shows that this object is somewhat ubiquitous in combinatorics as a whole, and you can get here in a variety of ways, and you can get to a lot of places from here. So let's go back to the mosaic. So we are reasonably sure that this particular mosaic can be generated from this particular permutation. But what about the reverse? Given a mosaic, could I have generated permutation out of it? I can play it in reverse, but like it's not as it's not as evident, because like calculating all the left shifts and the downshifts in reverse is we pop the top right and extend like that. Like that's not the case, because if you pop two, then like you extend one, and then you are saying pop one and then extend the 3 and 5. That is that's basically a stack algorithm, right? And that is exactly what I'm going to do, but I'm going to instead of creating it from the reverse, we are going to create it from forward. So let's read it back. Yeah, let's read it back. Come on. But before reading it back, I want to show something. There was a question like, hey, like, can we what would happen if I put this particular junction up and this particular junction down? Well, let's do that. Let's do that. Let's do whatever the hell we want. You know, this is the same object. And we can do everything, but we can't cross this particular line, because like sliding further would put 4 rooms around one point, which is no longer a mosaic floor plan. Yeah, Mondrian would be proud, wouldn't he? I love Mondrian, and I love like abstract and surrealist art. So like, yes, the Mondrian really would be proud. There's a lot of fun stuff, but there's also actually something subtle hiding here. The question is, you mentioned like, hey, let's pop the numbers from the top right, or the something like that. But how would you, if you were not given these numbers, how would you still get the permutation back? Any ideas? If you had the numbers, yeah, it's easy. Yeah, we're number blind. We cannot see the numbers. Two orderings. Elaborate, like you are like at the right answer, obviously, but elaborate. Um, if constructing the numbers as I go, like yeah, it's not obvious. Like just looking at it, I can't quickly get it. Like it's not very like just for 6 blocks, I can't do it in my head properly. For 10 blocks, I definitely can't do it in my head. Yeah, it's not straightforward, but there's a straightforward way of doing it. CTL 560. Do you wanna like elaborate on your idea? Yes, it can happen in a single linear pass. Okay, fair enough. Um, so the idea is to create a canonical arrangement of these rectangles. Um a canonical arrangement is an arrangement where every rectangle has its top left or the at the corner basically on the main diagonal. So no, I need to put this here. Yeah, this could be we are trying to satisfy a condition where the line passes through all the rectangles. The main diagonal line passes through all the rectangles. And the moment we get that, that's our ordering. There's a way to actually construct this, but like I don't remember the algorithm off the top of my head. But if imagine like so let's say that I don't like need a computer, but I can just mess around by hand and just put all the rectangles in order where like the line crosses through all of it. Suddenly I have my ordering. Um, and unpacked, we don't even need to pop and get the permutation because getting the permutation is as easy for a human as doing this. Do you see it? Do you see it? But like just for the sake of it, we can recover the permutation. Yeah. So let's reset the walls. Even if we didn't mess around with it, we could, let me zoom out a bit. We could recover the permutation just by popping the bottom left every time. So the idea is given any rectangle, if you know the numbers, you just pop the bottom left every time or the top right. Like, yeah. Kind of nifty, right? I think this looks pretty cool. Um, yeah. So that is the relationship between the permutation and the mosaic and the mosaic and the permutation. Because it's a one-to-one relationship, it is a bijection. And fun fact, the Baxter permutations don't just biject to the mosaics, but also other stuff. Yeah, so this is not needed. That is just a correspondence strip. I don't want that. Which one do you want to go next? The BBF graph, which is a plane bipolar orientation, the planar bipolar orientation, or a meander, or the twin trees. Which one do you want to go next? In order. Oh, all right. So this is called, like, the layout's a bit janky, but yeah, it's good. Yeah, that's the combination of the order. Nice. 2, 3, 4 is a Baxter permutation. Let's verify that. Yes, 1, 2, 3, 4 is a Baxter permutation. So we are in a Baxter permutation of the order here. Now, like, if we did like can anybody tell me, like, if where do I put the 5 so that this stops being a Baxter permutation? Is 5, 1, 2, 3, 4 a Baxter permutation? Well, yes. What about 1, 5, 2, 3, 4? Yep. 1, 2, 5, 3, 4? Yep. 3, 4, 3, 5, 4. Yep. 1, 2, 3, 4, 5. Yeah. So there is no place I can put the 5 where exactly. There is nowhere. Let's try to construct a Baxter violation. So, say, what about this? Okay, so what about the flippy? Yeah, so let's flip 4 and 3. I think that would be a violation. Nope, that still wouldn't be a violation because these two are. So what about 6 and 5? And we put 3 and 4. This should be a violation. Okay. And this popped up. Okay. So why is it a violation? Because um, we have 2 at position 3, 6 at position 4, and that between 4 and 3. So 3, 1, 4, 2 pattern. And we have a problem. So let's put in your 1. Yep. 2, 4, 1, 3 pattern. 3, 5, 2, 1, 4 has 3, 5, 2, 4, which is a 2, 4, 1, 3. And it is, yeah, it is like a polynomial. It's probably O of n cubed. Yeah, probably. Like, I don't like at least the naive algorithm definitely is. I don't know if there's. I think there's been research on enumerative combinatorics so that it's n squared log n on some patterns. I think Baxter somebody has gotten like pseudo linear as well. I don't know exactly. There's some like really clever use of stack, and the fact that we are like in a very limited space. But yeah, if it was if the adjacency condition was not there, then it would definitely be n cubed. Definitely. So the adjacency condition does help us a lot. Now we can actually like I have in my site I have this little nifty thing where if you hover over the draw, you can kind of see what's happening. Isn't that cool? I think it's cool. Right. Yeah. So, and this is the permutation matrix, and usually permutations are either written as like long strings of numbers like this, or matrices like this. And like matrices are quite interesting because it goes into something called and this is basically a limit of permutations. So if you take permutations as an object and as a probability space to the limit, then this is uh, like what you get. It's like there's been some really exciting research on the concept of permutons, and somebody in 2023 actually has discovered the Baxter permuton, as in the the limit of all Baxter permutations, and what probability structure does that take. That's again very cool. So let's look at this graph. I want to talk about this graph more. uh, what is this graph? Where is this graph coming from? Any guesses? Any guesses on what W2 and W3 and W5 is? The use of the word, the letter W might like give you the hint. Not quite. Not quite. Although there is some mosaic information hidden in this graph. So somewhat correct, but not like the W nodes themselves and the S and T nodes are not submosaics. And I'm using the same colors as the rectangles for a reason, for the edges. If you turn on wall graph, you can kind of see what's happening here. So I just overlaid the walls on top of the mosaic. And what I see is from the source, 1 goes to W2 and 5 goes to W5. From W2, 2 goes to W3. There's parallel edges here from W3 to W5, and from W5, it goes to the target. It helps us with primality, identification actually, because remember, like for a thing to be composite, like which actually kind of takes out a lot of the trivial primes, like a lot of the trivial composites. So, like any case where there's two vertices are next to each other, two blocks are vertically next to each other, they will always manifest as parallel edges. So if there's parallel edges, we are not going to be prime. Similarly, let's create another, like say 1, 2, 3, 4. Let's do 1, 2, 4, 3. Okay, so we can do something like this. So there's no parallel edges here, right? There's no parallel edges here, but if you notice, if you click this particular thing, this wall and this wall are pass-through walls, as in they are just next to each other, because they have one incoming edge and one outgoing edge. So any wall that has something like this or something like this will end up being a composite. So any degree 2 node or any parallel edges, and parallel edges by definition like also induces two connectivity, is composite. In general, it can be shown that any prime is actually always three connected in this graph. So what is three connected? Three connected means that you need to at least delete three vertices for the graph to be disconnected. That is tree connectivity. But you can look at this and say, like, hey, like if I delete W3 and W2, the graph's disconnected. So how is this tree connected? Well, the answer to that is that we are always considering a shadow edge between the source and the target. That like considering that shadow edge makes this a rooted planar bipolar mapping. What is bipolar? Because it has two poles, source and target. And it's planar because this is always going to be a planar graph. And mapping because every edge is directed and there's no cycles. So these are my three conditions for this graph to be made. And it can be shown that every backstep permutation can be a planar bipolar mapping, which in turn can be a mosaic. And there's a very easy way to move from a mosaic to a planar bipolar mapping. Right? So nested pinwheel. You mentioned nested pinwheel. So let's look at a nested pinwheel. How would that look like? I'm just going to paste this. This is a nested pinwheel, right? Is this what you were looking for? Can you quickly I can pull up your video actually. If pinwheel with pinwheel in the center. Okay. Maybe the duals of this. Like again, let me. Yeah, none of this. Okay, pinwheel with pinwheel in the center. How would that look like? Let's start with let's see if I can construct it from the so in here it's going to be a pinwheel, yeah. So 3 is going to be replaced by a pinwheel, yeah. I wonder if this can be as trivial as so if this is 3 plus yeah, I'm thinking of doing that. So if this is 41352, and then 5 becomes so 1 and 2 becomes so 6, 3, 5, 7, 4, and 41352. So 5 becomes plus 2 plus 5 is 10 and 2. 9 2. Oh no, I'm sorry. 4 becomes 9. 4 1 6 3 5 7 4 9 1 6 3 5 7 4 10 2. Am I missing a number? 8. Yeah. Is this what you wanted? I figured this out by reversing, like reverse calculation by putting in the permutation in the middle and bumping up the numbers. But yeah, so this, let's relax the layout. Um, so this is still connectivity 2, even though all of its degrees are 3 and 4. So, and that is why there is no pass through degree 2 and there are no parallel edges. You are like correct in the sense that just by looking at the degrees themselves, we cannot figure out primality. But if we have a graph, like a connectivity algorithm, we can if we can check whether a graph is k connected at any given time, we can test whether this is prime or not, because this is till 2 connected. And it is 2 connected exactly at source and target. So if you removed the source and target, then it will suddenly become like a split in a way that is hard to figure out. The condition equivalent to primality is for the graph to have connectivity 3. And connectivity 3 is so graph connectivity is yeah, there you go. So graph connectivity is asking for the minimum number of elements that needs to be removed to separate the remaining nodes into 2 or more isolated subgraphs. So because we can remove 2 vertices in this graph and make this a composite, and make this a disconnected graph, then therefore we can judge that this is composite. Even though it doesn't have any of the trivial composite markings. Yep. And these coordinates, like where the vertices are currently sitting, are also like meaningful. They correspond to a certain kind of lattice walks in the positive quadrant. So this particular mapping also corresponds to something called tandem walks graph. Yeah, so they correspond to something called a lattice path on the 2D integer grid, restricted to a specific step set. It's wild how everything is corresponding to everything. Yep, and tandem walks to map directly onto planar bipolar orientations, and planar bipolar orientations map directly to backstep permutations, and as well as mosaics. Quite wild. So that's this graph. I would like to talk about this or the twin binary tree. Like, does this look interesting? Let's do it in order. Let's look at this. Yep, tree connectivity is checkable in linear time. Yep. Actually, before I mention, there is also another way to check for primality. There is another way to check for primality that does not require us to stay in graph land. That is, what if we look at the permutation itself? There's a class of permutations called simple permutation. Please tell me there's a please. Okay, fine. We are going to okay. So no, that's not what I need. Okay, let's just generate like a prime. Okay, let's just generate a 7 length prime, and then we can like show the example of a simple permutation. 6152473. Yeah. No, it's not naively identifying the subblock. It's actually more interesting than that. Yeah, this is nice. Perfect. No more getting cut off. Remember like what the permutation was? It was 6152473. 6152473 at positions say 1, 2, 3, 4, 5, 6, 7. Right? So what I can do is 1 moves to 6. Well, then where does 6 move to? 6 moves to 7. Where does 7 move to? 7 moves to 3. Where does 3 move to? 5. Where does 5 move to? 4. Where does 4 move to? 2. Where does 2 move to? Back to 1. Do you notice something interesting? It's one single cycle, exactly. A simple permutation will be one single cycle. It will not have sub-cycles inside it. So, for a mosaic to be prime, that implies permutation is simple and Baxter. Ooh. Well, like it's not just cyclic. It's not just cyclic. Simple permutation is more than just single cycle. And it is also like if you remove any one of the elements, it would it might break it. It might break that cycle. So let me show simple permutations, the definition. Wolfram, maybe Wolfram has a better answer. Uh, mm, Special types. Single cycle which covers all items, or there are the trivial cycle. So either you have the full cycle or you have the trivial cycles of length 1. So that is yeah, maybe this is consecutive positions um, mapped uh, uh, not a block. Yeah, all its blocks are trivial blocks. No, 1, 2, 3, 4 is not definitely not prime. Then 1 maps to 1. It's a 1 maps to 1. It's a single cycle. We don't want single cycles here. It needs to be like the number of cycle needs to be this one particular cycle. So let's look at actual simple permutations. Simplicity. Okay. Yep. 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 And notice this particular like line is very much like in going in tandem with your um, conjecture about every mosaic being written as a way of composing prime mosaic. So yeah, so again, bijection. It maps, everything maps to everything. Inflation is basically pinwheel within a pinwheel, where the thing that we just did with the like initial pinwheel to make the nested pinwheel. We put in a permutation within a individual digit of the permutation and increase the numbers. All right. So that is just by looking at the permutation, you can check for simplicity. And so, like if it's Baxter and simple, boom, we have a permutation that's prime, and that also maps to this particular graph being three connected. Um, yep, 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 exactly. This maps to like mosaics are constructible by prime decomposition. This is saying an unique simple permutation. It does not need to be unique in our case, depending on like which direction you come from. But if you have a canonical decomposition like we showed, then each mosaic maps to a single permutation. And the canonical decomposition like deals with the diagonals and anti-diagonals. That's and the next thing that I want to go into is meanderings. Okay, let's look at this. I put all my numbers in here and I'm gonna slide in like I put all the numbers in the number line. 6, 1, 5, 2, 4, 7, 3. That's my permutation. 6, 1, 5, 2, 4, 7, 3. And I'm gonna slide in from the bottom. I'm gonna hit 1, then I'm gonna cross over and go to 2, then I'm gonna cross over and go to 3, then I'm gonna cross over and go to 4, cross 5, cross 6, cross 7, and out. This is a meander. So this is like a river meandering through this line. So each meander encodes a specific permutation. And we can kind of see why that would be the case, yes? A meander being in a permutation and a meander being encoded as the same thing. You can kind of see that. Like it's just a way of crossing and look pointing which points are we crossing in. And that becomes my order. The order in which I cross becomes my permutation. But there's something special about this meander. Yeah, the crossbacks are, well, like, yes. So this is a non-crossing meander in the sense that this is a non-crossing meander, yes, or also called a monotone meander. And why is it a monotone meander? It's because we can stretch and squish it in a way where the blue line can be a function of pure function of x and the red line can be a pure function of y. The question is, how do I stretch and squish it so that it becomes that? The answer is actually deceptively simple. Any ideas? Yes, but actually there's like a way to do this that makes it very easy to construct in the first place. Do you want to see the way? Here it goes. Yes, construct not this meander, but the meander where we have like the blue line being a pure function of x. So something wavy that does not ever have two x values have the same y value. And similarly, the red line becomes a pure function of y. So something wavy where it doesn't have the same y value for any two the same x value for any two y values. A pure function of x and a pure function of y intersecting. So this is the hint. Do you see the permutation matrix for this particular permutation? I'm just going to bump up each node here to say this times 2 minus 1. So 6 gets mapped to 11, 1 gets mapped to 1, 5 gets mapped to 9, 2 gets mapped to 3, and so on and so forth. Yes, I make the node the position in the matrix. And the transformation kind of looks pretty beautiful. I know, right? Yeah. I was playing with this for more than I would like to admit. Yeah, so, but this is how you do it. And notice that this is a function of y that does not have any equality. So if you kind of tilt your head to the side, you can kind of see this as a pure function. And similarly for the blue. Yeah, I multiply the axis bound by 2. And if you consider the whole thing as a permutation, then if you consider the whole thing as a permutation, including the like islets as the dots, then you can copy the complete permutation and you can create a new Baxter permutation that's not going to be prime, but it's going to be good. Yeah. And they just move from they always going to move from bottom to top for the red and from left to right for the blue. Red will always move from bottom to top and blue will always move from left to right regardless of anything. And you can kind of see this whole matrix, including the white dots, as another permutation that's not prime. So you can copy it and you can paste it in here and you can see the permutation. And you can kind of see that this is just the same permutation, but with the vertices, all the rectangles doubled except the middle of the pinwheel. And now now that we have the big permutation, then we have created something like this. Do you see it? And we can go back to the old one, I hope. No, we can't. Okay. Okay. But yeah, so this is meanders, and they are also very, very, very linked to Baxter permutations, as you can see. I know, right? Like these are really, really cool. These are really cool looking. I did a lot of this particular random prime searching. I do a lot of shit. I do a lot of stuff to get this to work. I for anything less than n equals 17. So anything less than 17, I have lookup tables and I just fetch uniformly from the lookup table. Anything more than that, I have actual enumeration like a sampler that runs in WASM. Like I wrote the program in C and then I compiled it in WASM, and so it's running in WASM, so it's fast. So if I do a 19 rectangle prime, it can generate pretty fast. And like if you want to see the meander first, let's uh, do that. Let's grab the Mosaic over here. Random generation, like if you're not using a lookup table, then it just enumerates all the backstairs and finds the simples. Yeah. Because simples are way more common than backstairs. So it enumerates the backstairs first and then like checks for simple. Um, Going crazy and put things like, say, I go as up to 200. I go up to 200, and beyond 20 and 21, I can't do normal search. I basically do MCMC search, and that too is compiled in WAPM and running here. So a Monte Carlo search is running like that takes in existing simple patterns and tries to build more simple patterns and tries to lap out. So the anything beyond 21, I cannot guarantee that the sampling space is uniform across all primes, but you'll still get a lot more variety than, yeah. So anything beyond 21, I can't say that if you click generate, you will get all primes. But it is, yeah. Yeah. So if you look at this, this is quite the doozy. I want to hit it. Do you want to hit it again? I know, right? Hold on. Please, please tell me that you didn't mess it up. Hold on. I also have this like a library called DocView that does the stuff. Oh yeah, I want it. Wanna see? Cool, right? And I have it bound to a hotkey called G. So if I press G, I can immediately get a different. Well, not maybe so immediately. Yeah, it's a different one. Did I break the hotkey? I hope not. Okay, it's generating. Yeah, so I think 200 is a bit too much to actually see the cool stuff. Let's try something like, say, 64. Yeah. And then you can kind of see things change a lot. Yeah, the larger Monte Carlo ones, I think like there's a lot of other um, patterns that it just can't figure out using the search algorithm I have. Yeah. There's like other stuff, but yeah, like I think it's also the layouting. I think it's also the layouting. The layouting that I'm using, it is like it is kind of wanting to branch out from the top left and generate these canonical forms. It's just in the lower scale, it's hard to see. So it's in 20, it's also doing that, but it's like hard to see because the scale is so low. Yeah. It's honestly like really fun to look at. Getting the transition right so that like during the transition it does not cross into like do crossings and like invalidate the topology was also a hassle. Also, there I didn't touch into something, but like there's also the dual of this. I think that is what you're looking for. I think these Baxter permutations have four-way symmetry. This might be like I should have probably led with that in at some point, but they have four-way symmetry, sort of a four-way symmetry. So you can do four duals and get back the original position. And that's because a permutation, you like each dual is basically rotating the permutation graph 90 degrees. So you create, like you rotate it four times, you get back to the original. I think my massive, like my MCMC is only doing the top left dual, not the, yeah. Yeah, so that's basically like the kind of stuff that you can see. Like it can be ascents and descents. So like number of ascents and the number of descents matter a lot when it comes to the primes and non-primes. Yeah, Meander is very cool looking. But I want to like hit the twin trees. Let's start with 7 prime maybe. Maybe the fun prime. So this is fun for a different reason, but I'm going to look into yes. Um, so let's the graph here. The the graph is the exact lattice of the octahedron, and this is also the first four regular graph. So, or like, and with connectivity 4. So this is genuinely a stronger prime in some sense. So this is one of the very few planar maps with connectivity 4, not just connectivity 3. So planar map with connectivity 3 maps to primes. Planar map with connectivity 4 map to super prime. Exactly. If you look at the thread in the Discord, I actually uploaded a sneak peek with super prime written on it. This mosaic is super prime. Yeah. So there are like I need to dig through the. Hold on. I actually want to show you something. Um, I want to show you something because I have. Yes, we can get even primer. We can get up to connected prime, but because we see connected, so 5 prime is the most we can get. And because like a primes map to planar, like yeah, fine, yeah, we can get up to 5, but we cannot get up to 6 because planar graphs cannot be like 6 connected. That's the theorem. And planarity like matters a lot because like we are directly mapping the permutation into a planar graph, not just a planar graph, but a planar bipolar mapping. Do you want to see the first 5 prime that I found? I'm guessing the answer is yes, so I'm gonna paste it. Let's see. Let's relax the layout because I put the thingies in here exactly at the like locations where the lattice coordinates should be, but that makes for not so fun graph viewing. So let's relax the layout. Well, that's not fun, but if you extend this, in a way that my graph library is not doing, you will get the exact lattice of an icosahedron. Hedron lattice. Um, so you will get this particular, not this one. Where's the lattice? Yeah, you'll get this. You'll get this graph, and this is the smallest 5 regular graph. This is the smallest 5 regular graph. So this is exactly what's happening, and the source is actually one of the interior, not the interior node, it's one of the corner nodes. But then again, this is completely symmetric, so it doesn't really matter what is an interior. The smallest rectangle that is drawn aligned somewhere over the mosaic will have to overlap with, well, kind of, not really. Like, yeah, like, yes, like that is definitely the case. Yes, because this is no. Yeah, if it's needs to be added, no, not in the bottom layer. If you see in the bottom layer, it is still 2. So like if you put it in the top or in the bottom, then it's still 2. Like, what do you mean by align? Like, maybe like I'm not understanding. So I was thinking here and here. So if you put a rectangle up here or a rectangle down here, is that what you mean by align? Okay, so like I think there's a different definition. Can you explain it? To check if a mosaic is prime, you can see if there is some subset of its triangles. Yeah, right. So there is no such subset because it's prime, right? So drawing a rectangle boundary on a composite matrix will cut through 0. I see. Okay, so if I want to draw a rectangle boundary, yes, I will at minimum cut through 3 like rectangle tiles. I have to. Well, not really. Like if I do this rectangle boundary at the top, like if we do like horizontal slicing, that's not the case, I think. But if you do vertical slicing, yes, that is the case. So, so horizontal slicing, nope. Vertical slicing, yep. And this makes sense because the graph edges, the graph nodes correspond to the vertical walls. So that makes sense that it needs to cut through 3, like the vertical walls need to cut through 3 edges. So it all corresponds. So if you look at the wall graph, so all the graph nodes of the graph are all the vertical walls. We are not really looking at the horizontal walls for the graph. So the graph's connectivity is a function of the rectangles and the vertical walls. Yeah, so this is cutting through the entire mosaic, right? Not so any small rectangle that does not cut through even a single wall. Well, it doesn't really matter, right? Because you can always stretch a wall to your cut point. You can always stretch the wall to your cut point. So as long as there are vertical walls to stretch to, it will like your closest wherever you decide to make the cut, I can always stretch the wall closest to it and be done with it. Or do you? You want something like this? Okay, like this. Okay, I see. I see. I see what you mean. Like you want something like this. Yes. You say this is fine. You don't need it to be like extending across the whole mosaic. You think this should be this should be fine. And if this is fine, then yes, it can cut. But like yes, if you are trying to find a vertical wall that cuts from the top to bottom, like a block of rectangle that cuts from the top to bottom, it needs to cut through at least three rectangles. And then it can use this wall so it doesn't cut through this fourth rectangle. So your definition, if you change it to yeah, but verticality like it matters because horizontality is just the dual of it, right? So if I just do the dual of this graph, and then it's the cubic graph. So it's the dual of the icosahedral graph, and it's the cubic graph. And it's the same story, just flipped 90 degrees. And it's three regular in our like in this space, but it is five regular in the like flipped graph space. So the vertical walls and the horizontal walls is actually the dual of these two graphs. So this is the graph for the vertical walls, and the dual of this graph would be the horizontal walls, where the faces are the vertices and the vertices are the edges. So there's a lot of symmetry and duals going on here. Okay, I'm going to finally hit the twin tree because I want to hit this particular bijection, and it's again I'm stealing from Don Knuth this particular lecture, and this is just you take the permutation, and our permutation is this 8271196315104, and we have two binary search trees. Okay, and for the left one we insert it from left through right. For the right one we insert it right through left, and we create two binary search trees. Okay, makes sense? And just for a reminder, a binary search tree is a tree where you have a root node, and anything left of the root node is than the element, and anything right of the root node is larger than the element. And so if we put in the numbers 8, 2, and then 7, 9, 11, 9, 6, 3. Let me just pull this up because I need this at the top. Better? Yeah. Okay, so 8, 2, 7, then 11 goes here, 9 goes here, then 6 is small, 6, then 3, then 1 goes from here to here, and then 5, and then 4. And there's also 10 that goes here. And if you look at it from this way, so then first comes 4, then comes 10, then comes 5, You get the gist. Yeah. So we are pretty confident that a twin tree can be encoded as any permutation could be encoded as a twin tree, but a twin tree is unique in the sense that you make them face to face and you will see what happens. Everywhere I did a left insertion, I did a right insertion in the opposite place. So left insertion, right insertion, left insertion, right insertion, left insertion. So yes, that's the magic of the twin tree. So twin trees are a direct bijection to Baxter permutations. Like it could, but like I can give you something better. I can give you the mosaic, and I can get you the twin tree out of here. Do you want to see that? All right. So this is my final animation that I have. This was my mosaic. Okay, mosaic's ready. What are my rules? My rules are every room becomes one node in each tree. The two copies are anchored at opposite corners of the same room. Okay? And the opposite corners being the top right and the bottom left. Okay? Top right and bottom left are the two corners. So we put a circle at the room's upper right corner, that's T plus. And then the lower left corner is T minus. Okay? And then what we do is we just look at all the T junctions. We just go horizontally and look at all the T junctions and we assign it to a particular like a edge of the board. Okay? The top corner goes to this one and the bottom corner goes to this one. For every tile, the top corner goes to this point and the bottom corner goes to this point. Iterating through it, you're kind of gonna see what's happening. Makes sense? Top corner goes here, bottom corner goes here. Okay? The next one is going to be this one. Top corner goes here, bottom corner goes here. Okay? Then this block. Top corner here, bottom corner here. This block. Top here, bottom here. Tell me at any point if it doesn't make sense. Now, do you want to see the magic? We have like assigned everything. Voila. And Don Knuth was very like amazed by this algorithm when it first came out in 1990, and because he was one of the earliest users of both the binary search tree as well as the one of the first people to mess with Baxter permutations as a combinatorics object. So the fact, I think, like this made him fall in love with Baxter permutations even more. There's a big chapter in his book of Art of Programming, Art of Computer Programming, on Baxter permutations itself, which is quite fun. And I haven't like looked into it properly, but I should. But yes, this is the very beautiful way to construct the twin tree from the mosaic. Right. So though these are all my um, um, like exploratory things, and all of them do exist at this particular website, um, and you can play with it. It's all client side. It doesn't really. It should all be fine for you to play with. And if you mess up the layout a lot, just click reset layout, and it should be fine. And yeah, um, it should be fine. You can kind of drag around and stuff, and like just play with it. And I think this is. I'm really glad that this exists, and if I could add more stuff to it, I would, because there are a lot more bijections to backstep permutations. So there's. I'm just going to show Jacobo Borga. Jacopo Borga, Baxter. So he has a very nice blog on Baxter permutations and the limits of Baxter permutations, and what structures come up as you take Baxter permutations and increase n until it hits a limit. So these are the Baxter permutation. These are like mosaics, which are also kind of one-to-one mapping with triangulations. Um, and then these are like lattice walks, and this is a structure that they have created called confor. I think it's called coalescent walks. I think. Mm, coalescent work processes. So, and because it's a continuous process, the coalescent work process, they can take limit of it and create the structure out of it, and then create a probability distribution for all the Baxter permutations. Quite cute. It's really, really, really interesting stuff. I really like it, and um, yeah. So I think this diagram enamored me towards meanderings. And there are other types of meanderings out there, but I wanted to replicate this diagram and the corresponding this diagram in a one single animation, and that was my motivation for it. I didn't go into coalescent works. I didn't go into the main algebra for it. I didn't go into how it ties into Liouville quantum gravity. I don't know what that is. I've seen a lot of it though, and I want to know more about it. Yeah, so people like it just go, the rabbit hole goes deep, and I can go further. I promise. And let me like the final thing that I can show before I end would be this is a program that uses the generating function for Baxter permutations and then inverts it, does something called a compositional inverse to get the number of prime mosaic or simple Baxter permutation in blazing fast speed. So if I save it as 200, and let's see if I can run this. Um, but this is like this particular formula is based off of the generating function of Baxter permutations. Um, okay, cool. Perfect. GP, let's share this window now. Mm, This is like a version of the formula I showed on the OEIS page. So this is the transformation of the formula I showed on the OEIS page. And the reason for that is that this transformation allows us to take out the guillotinable floor plans, basically floor plans which you can slice off clearly, easily. So that allows us to generate primes faster than the original genetic function, and definitely faster than the dynamic programming approach, which itself is very, very fast. Maybe like this. Okay, where is this? Maybe it's not in this folder. It's in. Okay. That's 1 through 200th of the prime enumerated in less than a second. So there are 2 primes at 5, 12 at 7, 24, 106, and so on it goes. And this particular number at the end, this is the 200 number of primes you can make with 200 rectangles. And I'll just name. You can see a parabola, yes. All right, I'm going to close the window. And that is it from me. This went on like longer than I expected, but like I had fun.